Right, so straight in with question number 1. So a lot of people still got these multiple choices wrong. First box that we need to be ticking is that calcium oxide is an example of a base. You need to know what happens when you have an acid reacting with a base, a carbonate, and also with a metal. Bases are insoluble substances that react with an acid. The second one that we need to put down is forces. We've most commonly put bonds as an incorrect answer. We're looking at electrostatic forces of attraction in an ionic substance, and continuing on that theme, while we're talking about ions, and this one here is asking you to give the charge on the ion. A lot of people didn't even say that there's a charge. That's the clue which one you need to be talking about. Anything about sharing electrons is not right in this case. So you get a mark for saying that calcium's losing and oxygen is gaining electrons. You need to get another mark for saying how many. It's 2 electrons, because one's got 2 electrons in the outer shell it'd like to lose, and the other one's got 6, so it'd like 2 to complete its outer shell. And then because of that, calcium gets a 2+ charge because it's lost 2 electrons, and the oxide is a 2- charge. It's alright to put the element symbol with a charge next to it, or write the word. You'd still get the marks either way there. Question 2. In this question here, a lot of information. The main thing that you needed to know, that this was asking about conservation of mass. So when it says you've got approximately 1600 going in and approximately 800 going in, that gives you approximately 2400. And here you've got about 2000. So the difference there is about 400, the mass of titanium. So if you actually put the numbers in and do that properly, you get an answer of 408 kilograms. It's showing that the amount that goes in, the amount that comes out is the same thing. Nothing is gained or lost. For the next question on the graph, you need to have plotted your points accurately. The scale is where most people lost the marks here. If you look at the first point, 35.72, that is approximately 35.75. If we look at where that should be in reality, there's 35.5, there's 36, so 35.75 would be halfway in between. It'd be this line, so we'd be looking at your points be there. Most commonly people are out by more than a bit. You just need to practice your points. It's a math skill. A lot of people were out on more than 1 point, so if you were out on 1 point, you lost 1 of the marks. If you're out on more than 1 point, you lost 2 of the marks, and then the third mark was dependent on you drawing a line of best fit, and they were also quite poorly drawn. The line of best fit needs to go as close to as many of the points as possible, and there was 1 point which was clearly an anomaly, which did not fit the pattern, so you didn't want to bend your line of best fit to try and incorporate that. The next question. In this one, you're trying to work out the volume of water needed to dissolve this substance. Now it says if you've got 36 kilograms, you'd need 100 decimeters cubed. That's the same as a litre, so 100 litres. So for 2, you'd need 72 kilograms. You'd need 200 litres or 200 decimeters cubed. So what we're basically seeing is how many times that 36 kilograms will fit into 1989. The issue that you've also got there as well, this is per 100, so what you'd need to do is include a times by 100 to show that you're getting into, so you're taking that into account. It's not 36 kilograms per litre, it's 36 kilograms per 100 litres. So when you do 1989 divided by 36, you've got to times it by 100 afterwards. So the correct answer is 5,525. And a lot of people got it wrong because they might have put 55.25. So you're off by a factor of 100 because you didn't take this bit into account. Which is a bit of a tricky one, to be honest. Next question down. A couple of bits to look at here. When you're calculating the percentage mass of titanium chloride, the first thing that you'd see on a question like this, I've got titanium and chlorine, I've got the atomic masses, let's add them all up and get our first mark. So that's going to be titanium 48. And it's going to be 4 lots of 35.5 because there's a little 4 there. So the total is going to be 190, have your first mark. The next thing we need to know is how much titanium is there in titanium chloride. So titanium was 48 parts out of the 190 in total. So 48 out of 190 times by 100 to turn it into a percentage would give you 25.26. But that's only 2 of the marks, because here it says I need 3 significant figures. The first significant figure is 2, and then it is 5, and then it is a question of do I leave it as a 2 or round it up to a 3. Of course, you round it up to a 3, so it's 25.3 to get the full 3 marks. Show your workings on it, and then if you do get something wrong in it, you can get credit for that bit that you did get right. This one here, bit of a mean question. Loads of people weren't being specific enough for it. So it says, suggest why the reaction done in an atmosphere of dry argon. So the first word there that you're looking at highlighting, dry. Why is it going to be dry? Well, if you look at the mark scheme, there's an idea. If it's not dry, it could be wet. And if it's wet, then that could be a problem because the water or the water vapor could react with the sodium or it could react with the titanium chloride. What the mark scheme is asking for there is specifics. So you don't want to say something like the water made it heavy, and you don't want to say something like the water may react. It's actually asking you to say what you think might happen, which is quite specific and quite difficult for an answer. The next bit says, why is argon used? I've hopefully prepped people in this one in my lessons when I'm saying if they're asking anything about argon, which is a noble gas, it's because it's inert, it's unreactive, it's got a full outer shell. And then the last bit, it says, instead of air. So what's in air that could react? It's the oxygen. So again, what you need to say is not just that the oxygen may react, that you may want to say that the oxygen is going to react with the reactants instead. So that's the problem that we're looking for. Okay, it's allowed that you said the oxygen could react with the products as well and could affect your investigation that way, but you have actually got to be specific. You can't just say oxygen may do something. Final question. It's got a cheeky bit in it as well. Titanium conducts electricity. Titanium's a metal, so it's just asking why do metals conduct. It's been very specific in the mark scheme here. It says that you've got delocalized electrons. So if you wrote spare electrons or free electrons, that's not what the specification says. And in your lesson that we're doing, it does say that there is a sea of delocalized electrons. So there's your first point that you need to be putting. You can then get a mark for saying because they're delocalized, they're able to move or they are free to move. That's the second idea, this concept that they're moving or flowing. And then the last mark, which is quite a cheeky one to slip in, is to say that they're going to move through the whole structure, which to be honest is quite a difficult point for you to put in structure unless you've been primed for that. On question 3, first one, radius of an atom. So if it was in the first two sizes, it means that an atom is going to be big enough that it's going to be within the size of a meter ruler that you'd be able to see. And atoms just aren't that big. So this is a question just saying, do you know what standard form means? And the scales of 10. So every time I'm adding a -1 up here, I'm getting 10 times smaller. So I'm moving the decimal place along 1 point. So that's 1 meter. That's 0.1 meters. They're too big. 10 centimeters for this answer is too big for an atom. So this one is going to be 0.000000001 meters. So I've moved the decimal place back 10 times. That's about a nanometer. Sorry, it's just under a nanometer. That's the size for an atom. At 10 to the -100, it's far too small for us to be measuring or looking at in any particular way. So it's just completely out of the picture. So this question is referring to figure 4 and not figure 3 like the question says. These are not the symbols of the elements, and if you look, they have 3 electrons here, so that would be 2 in the first shell, 1 in the outer shell. This one's got 2 electrons in the first shell, 8 in the next shell, that's 10, and 1 in the outer shell. These have all got 1 electron in their outer shell. That means they are all group 1. The other way you could get this is by looking and finding some of these numbers on the periodic table and realising that these are all elements in group 1 by looking at the periodic table at the front of the exam. When it asks which ones are isotopes, it is R and S. If you look at R and S, it is because when you look at their atomic masses and their atomic numbers, they've got the same number of protons by the 3 protons at the bottom, and S has got an extra neutron changing its mass by 1. So you need to talk about both the number of protons or the atomic number and the number of neutrons or the mass number. For question 3, part 4, the halogens are in group 7. Explain the trend in reactivity. Generally very poorly answered this one. Some people just went along the lines of they are reactive. The question says there's a trend. So for very simple 2 marks, what you might be looking at is full sentences using good English saying that as you go down the group, the reactivity decreases, or as you go up the group, the reactivity increases. Getting above that and beyond that, we're looking at some explanation. So it might be that you're saying that the smallest element at the top, fluorine, is the most reactive, and the largest at the bottom is the least reactive. And then the top end answers, you're telling us in a logical order, quite specifically, why that affects it. So in the smallest fluorine, the electrons that are being gained are going to be strongly attracted because there's very little shielding. Or the opposite applies as well. At the bottom end, the largest element has the most shielding between the electron it's gaining and the positive nucleus, which means that there's going to be a weaker force of attraction, so it's going to be much less reactive. So the electrolysis question was, again, a difficult question for pupils to answer. When we're looking at what we should draw in the diagram, it's two simple points. First of all, electrolysis is splitting using a DC power supply, and it says that in the question, DC power supply. To show that it's DC, you could label that the box that you've drawn your wires to is DC, or you could show that there is a plus and a minus on the terminals. Just a box with some wires come out of it could be providing AC power, which is not the same thing. The other thing you need to label is the electrodes that are in the solution, so that would be the anode and the cathode. You can put a plus or a minus next to them if you wanted to, but that's the main thing that we're looking for. For parts 2, the colour is going to be down to the copper ions. When we talk about electrolysis, your answer has to refer to ions. If it's not talking about ions, which is really specific from AQA here, it's not talking about ions, they're not interested in what you've got to say. So the first mark, the copper ions cause the colour. The second bit they're looking for is that the copper ions are being reduced. Remember, oil rig reduction is gain of electrons. Or if you don't want to talk about the electrons, you could say the copper ions are losing their charge and they're being turned into just plain copper. The last point that you're saying there is, because the copper ions are no longer in solution, because they're being taken away and turned into pure copper, there's less copper ions in the solution, so there's less colour. You can't just say that it's being used up or taken away. Again, in the same theme, this next question, low scoring, not talking about ions, not scoring marks. So you'd have to say that copper ions are positive, they are cations. The second mark, you'd have to say that they are attracted to the negative electrode or to the cathode. Bonus if you're saying words like like the mark scheme says. Third mark you can get is by saying what the ions do at the electrode. So the positive cations are going to gain electrons from the negative electrode. You don't need the full sentence like that, but obviously that shows a good understanding of what's going on. And the last mark is saying what that means. So if you are gaining electrons, remember oil rig reduction is gain, so they are reduced to form copper atoms. This next question, again, I see here that I've been given something to talk about, and I've been given the relative atomic masses. So the first mark that you should do, if you're going to get a mark, which is the only mark that most people got, is to add them up and find out that copper sulfate has got an atomic mass of 159.5. Whenever you get one of these questions, if it's difficult, just add up the numbers to get the formula that they're asking you about. So, it says in the question there that you've got a concentration which gives you 80 grams of copper sulfate per litre. And we've got 50 centimetres cubed of a solution. So we need to turn that into decimeters first of all by dividing that by 1,000 and see how many times that fits into a litre. That means that we would get about, in 50 centimetres cubed, we'd get about 4 grams. Okay? 4 grams. Then we can use our formula to work out the number of moles. So the number of moles is always going to be the mass in grams, which is 4 in this case, divided by the MR. It's 4 divided by 159.5 will give us a number of moles. When you get that number of moles, to find out how many grams you've got of our other substance, you would then times that by the atomic mass of our other substance, which in this case is 56. So you'd get your answer from 4 divided by 159.5 and times it by 56 to turn it into how many the mass of iron that's there from the moles of iron, which would give us 1.40. There's your number there that carries on in your calculator. The mark scheme here has simplified that equation down and not explained that they've turned that into a number of moles. The last mark is for giving the right number of significant figures. It says 2 significant figures. The first significant figure is 1, and the second significant figure is 4. Question 5. A lot of people did good by putting a dot and a cross in between the hydrogen and the chlorine in the overlap to get the single mark that they've given you on this one. Not only do you need that pair of electrons there, a dot and a cross, but you also need chlorine's other 6 electrons in its orbital, which would make 7 for chlorine, it being in group 7 in total. There's only 1 mark available for that, which is quite tough. This question here is asking for the difference between a weak acid and a strong acid. First thing you might say in the definition, a weak acid is a weak acid because it only partially dissociates, or a strong acid is a strong acid because it fully dissociates or fully separates. They're little definitions for you. Talking like that gets you in towards the top end marks. Right from year 7 though, on the early easy marks, you can say something nice and straightforward, like you could use universal indicator. Strong acid would make it go red, that's a pH of 1 or 2, and weak acid would make it go sort of like a yellow or orange, pH 4 to 6 sort of territory. It can't say litmus because it only goes red or blue. It doesn't give you any indication of the strength of the acid. Another alternative you could say is pick a metal like magnesium and then explain what you'd see in a difference between a strong acid and a weak acid. Stronger acids would see more of a reaction, more bubbles, and then a weaker reaction would see less bubbles. So a level 1 answer, simple statements like using universal indicator and a colour that it might turn. Level 2, for 3 to 4 marks, then you'd be giving me more details. It might not be 100% precise. You might be talking about magnesium and being used and bubbling and seeing a difference, but not being very specific what you'd see in a difference. And 5 or 6 marks, you're comparing both reactions in a nice logical sort of way. You're also including the idea of ionization or dissociation, where acidity is down to the hydrogen ion concentration. More hydrogen ions, more dissociation, stronger acid. Question 6. First thing it's asking you to draw is the energy profile highlighted here on the mark scheme. First mark for putting the reactants and the products as 2 horizontal lines with the reactants on the left higher than the products on the right. Second thing is for showing the energy changes. So you've got the activation energy as the height, the initial kick to make it move, and then the overall energy change is the energy change between the reactants and the products. For part 2, some people had a good stab at working this one out. Every time you see a C and an H joined together with this little stick, each one of those is worth 413. So there's 413, another 413, another 413, another 413. That one there must be worth 498, and there are 2 of them. Add all those together, we get our first mark, 2648. Same for this side, find the strength of this bond. There it is, there's 2 of them, add them together, and then find the strength of this bond. There's 1, 2, and there's 2 lots of those, there's 4 lots of them. Add them all together, we get 3466. Don't do what the mark scheme says here because it's the wrong way round. If you're actually looking at it properly, it should be 2648 minus 3466. The real reason for that is I absorb 2648 joules of energy to break the bonds. I'm putting in the energy to break in the bonds, and then as the new bonds are being formed, I'm releasing 3466. That is, more energy is going out. 818 kilojoules of energy is being given out. It's an exothermic reaction, so I'm losing energy from the system. As the graph there shows, I start off there and I'm losing energy to get to here. I'm losing it minus 818. I'm taking away 818. So, question 6 part 3. 6 mark question. Key thing here, it says exothermic and it says safely. So get your first marks for talking about simple things like goggles and how to handle acids safely, and you can get into your first 1 or 2 marks. Knowing that exothermic means giving out heat should instantly start making you think about thermometers. So you'd be looking at using a thermometer to measure the heat of the reaction. To work out which is the most reactive, it'd be the one that gives out the most heat energy. So then you need to start putting yourself into a logical order. At level 1, you might be giving some ideas about how to stay safe, and you might be talking about a thermometer. At level 2, you might be saying you need to measure the temperature to see which is the hottest. At level 3, you're given a nice order which makes it a fair test and stays safe. So something like measuring out the same volume each time, like 25 millilitres of acid, weighing out the same mass each time, like 1 gram of each substance, then reacting it for 30 seconds, same time each time, and then measuring the temperature change. And the biggest temperature change would be the one which is the most reactive. On this one here, a lot of people missed that it says justify your answer on 6.4, so the correct answer should be W, Y, X, Z. The justification for why it'd be W, Y, X and Z is, first of all, W reacted the most and Z didn't react at all, which puts them in first and last. And then in between, we had a few bubbles produced and gas bubbles, which means that Y is more reactive because there's more bubbles. So that explanation about more bubbles would put them in the right order. So there'd be a mark for each of those things. Putting them in the right order, and it does tell you there with the little crocodile symbol that you've got the most reactive on the left, right through to the right where it's the least reactive. Unless you labelled it differently, putting them in the wrong order would get it wrong. And the final bit. Tough question, this one. It does say in bold, though, the student is not completely correct. It doesn't say that they're incorrect, it says not completely. So for most of this answer, we're backing up what the student said. This time we're not talking about W, X, and Z, we're talking about the metals. So when you look at the solutions this time instead of the letters, magnesium is the most reactive because it is not displaced by any other metal. It is not reacting with anything else. Zinc is the second most reactive because it's displaced only by one metal. Now for copper and hydrogen, you can't place them in order based on the information that's in the table because you can't see which one's being displaced. So the further investigation that you'd want to prove the student being correct or incorrect is to put copper and hydrogen together in a chance where they can react or not to see which is the most reactive. So copper we can have as copper on its own. To get the hydrogen, one of the things that the exam board's looking for here is the top end thinking from the superstars, the very brightest. Your hydrogen is based from is hydrogen ions, hydrogen from acids. So when you have an acid, it gives out hydrogen ions to a solution, and there's a chance that they would react. So if we put copper and an acid together, copper and hydrogen ions in an acid, you can see if they're going to react, and you and I both know that copper won't react with an acid. It's unreactive, which tells me that hydrogen is more reactive than copper. It is not going to get displaced by copper.